Welcome back, everyone, to the Algebraic Graph Theory Seminar. This week, Mark Kempton from Brigham Young University is going to be telling us about cospectral vertices and isospectral reduction.
All right. Well, thank you, Max, for the introduction, and Sophia for the invitation to speak at this seminar. It's a privilege to be able to talk to you all today. So, like Max said, I'm going to talk about cospectral vertices and isospectral reductions. Now, if you have been attending other talks in this seminar, you've probably seen cospectral vertices show up a number of times. And so I'm going to talk about a connection between cospectral vertices and another tool called an isospectral reduction, and talk about some ways that potentially could be useful. So I'm going to start off with a definition that I suspect most of you are pretty familiar with. So we say that two vertices are cospectral if their adjacency matrices have the same eigenvalues. All right, so the study of cospectral graphs is a pretty big area in spectral graph theory. You know, in spectral graph theory, we try to understand graphs by way of their spectrum, the eigenvalues of their adjacency matrix. And so when two different non-isomorphic graphs have the same spectrum, this is in a sense giving us some information. It's revealing something that the spectrum can't really capture about the graph. So here's your, the classic first example of a pair of graphs that are cospectral to each other. So if you take this square with an isolated vertex in the middle, you write down its adjacency matrix, compute its eigenvalues, you get these numbers. If you take this star on 5 vertices, do the same thing, you'll get the same numbers. Okay, so the spectrum can't distinguish these two graphs. So we're learning some things that, the spectrum of the adjacency matrix can't tell if a graph is connected or not. So it's kind of revealing a limitation about what the spectrum is able to tell you about the graph. Now here I'm talking about the adjacency matrix. There are lots of matrices that get studied in spectral graph theory that you can associate to a graph. You can ask about graphs that are cospectral with respect to the Laplacian matrix or the normalized Laplacian or the distance matrix. There's lots of different matrices you could study. But for today, I'm just going to stick with the adjacency matrix. Okay, so this leads us to the definition of cospectral vertices. So we say that two vertices in a graph are cospectral to each other if G minus U and G minus V are cospectral graphs. Or in other words, if the characteristic polynomial of the adjacency matrix for G minus U is the same as the characteristic polynomial for the adjacency matrix of G minus V. Okay, so the question kind of arises, how can cospectral vertices appear? The most obvious way that you can have cospectral vertices is with symmetry, right? If I have an automorphism that maps U to V, well then U and V are indistinguishable. So if I delete U, then I get a graph. If I delete V, I get the same graph. So G minus U and G minus V are actually isomorphic graphs. So of course they will be cospectral graphs as well. So they will have the same spectrum. So symmetry is the most obvious way you could produce a pair of cospectral vertices. Here's another example where I guess the point of this example is to point out that you don't necessarily need an automorphism between two vertices to have G minus U and G minus V isomorphic to each other as graphs. So here, if I delete the vertex U, I get this, I get this path on two vertices together with this path connected to the triangle. And if I delete the vertex V, well, it turns out that I get this path connected to this triangle and an isolated edge there. So here G minus U and G minus V are isomorphic as graphs and therefore cospectral graphs. So U and V are cospectral vertices. So the point of that example is just to point out there's no automorphism here taking U to V or V to U, but G minus U and G minus V still are isomorphic to each other. But, this property that G minus U and G minus V are isomorphic is also not necessary. They just need to be cospectral. So how could that happen? Well, one of the classic constructions of pairs of cospectral graphs is this Godsell-McKay switching operation. I won't really go into what that is, but I suspect a lot of you are familiar with that already. But the idea is that if I have an equitable partition, I can attach a vertex to if I have an even number of parts here in this regular graph, right here I have this, this 8 cycle around the outside. If I attach a vertex to half those vertices, that is a cospectral to the graph that I get if I attach the vertex to the other half of those vertices. And that's the kind of classic Godsell-McKay switch operation for producing pairs of cospectral graphs. So if I just include both those vertices, then I'll have a single graph that has a pair of cospectral vertices to each other. So this is a way you can create infinite families of examples of things that have cospectral vertices that don't necessarily have any symmetry. G minus U and G minus V probably won't be isomorphic to each other most of the time here. And then there are some other examples. I've included 2 examples here. And in each of these examples, the vertices that I've labeled U and V are cospectral to each other. So here, U and V are cospectral to each other. In this graph, U and V are cospectral to each other. I include these examples because I think of these as sort of ad hoc examples that are they're kind of just by coincidence. I don't have a very good intuitive way of explaining why these pairs of vertices are cospectral to each other. I mean, it's easy enough to verify that they are. You just write down the adjacency matrix for G minus U and for G minus V, compute the spectrum, and they'll be the same thing. But I don't really know of a good intuitive explanation as to tell you ahead of time why that was going to be. Like I wouldn't necessarily expect that to happen just by looking at the graph. So I think a big important question is, can we characterize when 2 vertices are going to be cospectral to each other? Now, the answer to that is, in a sense, yes, and there are many characterizations of cospectral vertices. So here I've included a theorem that contains a list of statements that are equivalent to U and V being cospectral. So G minus U and G minus V have the same characteristic polynomial. That was basically the definition. You can characterize this in terms of walk counts. This is maybe the most interesting from the combinatorial perspective, that 2 vertices are cospectral if and only if the counts of closed walks at vertex U and at vertex V are the same for all k. This implies that U and V have the same walk generating function. And another equivalent statement is that if you look at the spectral idempotence in the spectral decomposition of the adjacency matrix, then the diagonal entries at each of those spectral idempotents are the same at the diagonal entries corresponding to U and V. So we have some important ways of characterizing when 2 vertices are cospectral. And and this list could go, I could include more things in this list. There are various other results. There's if U and V are cospectral, there's some orthogonal matrix that commutes with the adjacency matrix that interchanges U and V. And there's lots and lots of statements that are equivalent to two vertices being cospectral to each other. But I feel like the question is still maybe a little bit open in terms of what does this mean? If I just look at the graph, is there a way to just look at the graph and tell if two vertices are cospectral to each other? I think this is still an important question to try to answer, to try to give a full characterization of this. I'm not going to answer that question today, but I am going to give another characterization of cospectral vertices that perhaps helps give some intuition as to what this means. Before I talk about that, let me mention there's a strengthening of this property of two vertices being cospectral called strongly cospectral vertices. Basically, you just strengthen this condition rather than just ask that the diagonal entries be equal. You insist that the actual column of the spectral idempotent is plus or minus the column of the spectral idempotent for V. This is an important strengthening of the notion of cospectral vertices. So before I get into the real results or anything, maybe just let me argue a little bit for why it's this is an important thing to study. I would suggest that studying cospectral vertices is inherently interesting. Like I said before, understanding cospectral graphs and cospectral vertices is sort of fundamental to understanding what it is the spectrum of a graph can, of a matrix can tell you about a graph. So I think it's inherently interesting. Now, having said that, I feel like most of the study of cospectral vertices specifically has been motivated by this application to quantum state transfer in a graph. I know a lot of you are already familiar with this, so I'm not going to dwell on all the background of this application, but the problem of transferring a quantum state from one position in a network to another basically boils down to understanding this matrix, the matrix exponential e to the IT times the adjacency matrix. We say that there is perfect state transfer from U to V if the absolute value of the UV entry of that matrix is equal to 1. And the theorem here is that strong cospectrality and therefore cospectrality is a necessary condition for there to be quantum state transfer from U to V. So in this literature of trying to construct networks in which quantum state transfer happens, a sort of first step is to construct networks in which you have a pair of cospectral vertices. Just to give a slightly different perspective on this, so this e to the ITA, if there's perfect state transfer, then at the time at which that happens, e to the ITA is a symmetric unitary matrix. So it will end up having this block diagonal form here, where alpha here is some unit complex number, right? So if there's PST from U to V, then at time t, then this will be true. And alpha here is a unit complex number. Okay, so the reason, one way to get at the reason that cospectrality is necessary is to say, well, okay, if e to the ITA has this block diagonal decomposition, well, any eigenvector of the adjacency matrix is also an eigenvector of e to the ITA. So if you restrict those eigenvectors to this upper, these two vertices, U and V, well, those eigenvectors have to work as eigenvectors of this matrix 0, 1, 1, 0. And then it's not too much from there to see that that implies that the vertices are cospectral. All right, so that's one of the big motivations behind wanting to understand cospectral vertices. Okay, let me shift gears now and talk about something called an isospectral reduction of a graph or a matrix. So given a graph with a particular adjacency matrix, and really you don't need the graph for this definition. You can define the isospectral reduction of any matrix. So you take some matrix and you take some subset of the index set. The isospectral reduction of A onto that subset will denote with this R sub S of A. And this is defined by, so the A sub SS here is the S by S submatrix, principal submatrix of the adjacency matrix. So you take that submatrix and you subtract A sub S S complement times A sub S complement minus lambda times the identity inverse times A sub S complement S. So here lambda is just some indeterminate. It's some variable that we're sticking in the matrix. And this is what we call the isospectral reduction. If you're familiar with Schur complements, this is really just taking the Schur complement of A minus lambda times the identity relative to that particular subset S. Okay, so the significant thing about the isospectral reduction, I guess one thing to point out is that the isospectral reduction is going to be an S by size of S by size of S matrix whose entries are rational functions in the variable lambda. So, you know, you might get entries that look like this, or they might be very complicated, but, you know, as you compute this, the result is going to be some smaller matrix whose entries are rational functions in this variable lambda. Okay, so the one thing that makes these significant is that in a sense, the spectrum of your matrix is preserved by this isospectral reduction. So if I look at the determinant of the isospectral reduction minus lambda times the identity, and lambda here is the same variable lambda that I used in the definition of the isospectral reduction. Well, this is equal to the characteristic polynomial of the original matrix divided by the characteristic polynomial of the submatrix, the principal submatrix of A corresponding to the complement of the set that I'm reducing down to. Okay, so if by chance the submatrix does not have any eigenvalues in common with the original matrix, and this happens quite often, this is in a sense kind of generic, if those two matrices don't share any eigenvalues in common, then the spectrum of the isospectral reduction, where by spectrum I mean the roots of the determinant of the matrix minus lambda I, that spectrum is the same as the spectrum of the original matrix. Okay, so so it's in a sense a spectrum preserving operation. It's a little counterintuitive because you're squishing your matrix down to a smaller matrix. How could I preserve the spectrum? And the answer is that this matrix has entries that are functions in this variable lambda. So I can get more eigenvalues that way. And like I said, sometimes you do lose some of the eigenvalues if by chance this principal submatrix shares eigenvalues with the original matrix. Okay, Now, one cool thing about the isospectral reduction is these authors, Buminovich and Webb, they've kind of worked out some combinatorial rules for how to compute an isospectral reduction by hand, as it were, just looking at the graph. So if this is easiest to describe while looking at a weighted directed graph. So if I have a path from between two vertices, and in each of these cases, say this is my graph, and the red vertices here are vertices that I am reducing down to. They're vertices that belong to this subset S on which I'm doing the isospectral reduction. Well, when I do this reduction, so I can think of the resulting matrix, this RS of A is some matrix whose entries are functions in this variable lambda. And I can think of this as corresponding to a weighted directed graph, right? I can think of this as being this graph with edge weights being these rational functions in lambda. So what I'm describing here is if I start with a graph here and I apply this isospectral reduction, what happens in the matrix? Well, in the matrix reduction, the entries corresponding to these weights follow these rules. So if I reduce along a path between two vertices, then the weight on the edge between those two vertices is the product of the weights along that path divided by lambda minus the weights on any loops on the vertices in that path. And then if I have two different paths between two vertices, then in the isospectral reduction, the weights of those on those paths add together. And then an important fact here is that if I have two subsets of my vertex set and one nested inside the other, then the reduction onto the smaller subset is equal to, I can first reduce down to that bigger subset and then further onto that smaller subset. So I can kind of, if I have a graph and I want to isospectrally reduce onto some subset, I can kind of take it one vertex at a time. I can reduce down to the subset that has everything other than one vertex, apply these rules in this kind of combinatorial way to get this weighted graph that's smaller, and keep going down till I get down to my subset. Okay, so just as an example, to keep the example pretty simple, I'm doing a fairly small graph, but here's the complete graph on three vertices. If I want to compute the isospectral reduction onto those two vertices, well, I look at the paths between those vertices. So I have this path here and this path here. And in the reduction, between these two vertices, I'm going to have these edges. And since this is an undirected graph, I will get the same thing going in each direction. So I'll get these edges that are weighted by the sum of the weights on these two paths. This weight is just 1, and that's where that 1 is coming from. And then the weight on this path is 1 over lambda, because I take the products of these weights, which is just 1, and then divide by lambda minus the weight on any loop here. There's no weight, there's no loop there, so that has weight 0. Okay, so just applying these rules to this gives me those weights here. And then I also think about the weight on this loop, and the intuition here is that I have, as a path from this vertex to itself, I have this path here. I need to be looking at paths that don't involve the vertex in the subset until the very last step. So I have this path that goes from here to here, and that gives me the 1 over lambda as the weight on the loop at that vertex. Okay, so I guess the point is that there is a way of viewing this just from the combinatorics of what's going on. Okay, why do people study isospectral reductions? This can give improved bounds on spectral estimates. So for example, Gershgorin disks or similar kinds of estimates on eigenvalues often become a lot sharper when you apply them to the isospectrally reduced matrix because you are looking at a smaller matrix. Isospectral reductions have been used to study the stability of dynamical networks, uncover hierarchical structures in graphs. And then to me, the most interesting use of these isospectral reductions have been to study what have been termed hidden symmetries in a graph. So often what happens is you'll have a graph without any symmetry, and you'll compute the isospectral reduction down to some subset of the vertices. And once you've done that, that smaller graph does have an automorphism. And Smith and Webb call these hidden symmetries. And there's a good number of papers that study hidden symmetries in real world networks via these isospectral reductions. Okay, so kind of the story behind this, so Ben Webb is a colleague of mine here at Brigham Young University. And as I was applying for a job there, here, I gave a talk about this quantum state transfer problem and talked a lot about cospectral vertices. And he was in the middle of thinking about isospectral reductions and all these hidden symmetries. And, you know, as he heard me talk about cospectral vertices and how this is kind of, cospectral vertices are a generalization of automorphisms, he thought, I wonder if this has anything to do with these hidden symmetries that we've been studying. So we decided to think about it a little bit. And lo and behold, we were able to prove that these hidden symmetries and cospectral vertices are really the same thing. So the theorem is that U and V are cospectral to each other if and only if the isospectral reduction onto those two vertices has an automorphism. So reducing all the way down to those two vertices does produce a graph with one of these hidden symmetries. So we've added some statement to the ever-growing list of things that are equivalent to a pair of vertices being cospectral to each other. Let me give you some idea of how the proof of this statement goes. The proof I'm going to show you actually isn't the easiest proof, but I feel like it's instructive in terms of what's really going on with isospectral reductions and everything. So first of all, what we're really going to prove is that if two vertices are cospectral, the isospectral reduction onto a single vertex, the single vertex U and the single vertex V are the same. And it's not too hard to show that if that's the case, then this 2x2 matrix has an automorphism. Okay, so the idea here is to understand what's really going on with the isospectral reduction. So this here was the definition. And then in this next step, I'm just moving the lambda around a little bit. Now, if you're like me, whenever you see an I minus a matrix inverse, you can't help but replace it with a power series. So we replace this I minus this matrix inverse with the infinite geometric series. And we do a little bit of simplification and we get this. Now, anyone familiar with spectral graph theory knows that when you take powers of an adjacency matrix, what you're doing is you're counting walks, right? So the entries of this matrix right here are counting walks of length j, walks inside this, the complement of the subset of these vertices. Now here, this A sub S S bar is saying, well, let's take a step from my set S outside of the subset. And then here we're saying, let's take a walk of length j minus 1 outside of the subset, and then we'll take one last step from the complement of the subset back into the subset. So what this is doing is this is counting walks that, so I have my graph, right? And I have some subset S. I'm counting walks that leave the subset on their first step, walk around outside of the subset, and then come back to the subset on their very last step. So the isospectral reduction is really the walk generating function for that counts these non-returning walks in the subset. Okay, so once we understand that about the isospectral reduction, then the proof of our result is really quite easy. So we already said, okay, so one way to prove our result is that we want to prove that these non-returning walk generating functions at U and at V are equal to each other if and only if the walk generating functions at U and V are equal. So we mentioned toward the beginning that these walk generating functions are equal if and only if the vertices U and V are cospectral to each other. Once you've reduced it down to this, it's just a matter of thinking through the combinatorics. So you can express all of the walks of a given length, the closed walks of a given length at the vertex U, in terms of these non-returning walks, the walks that go away from U and don't come back to U until the very last step. And this gives you, if you think through it, this gives you a fairly nice, relationship between these two generating functions. So W sub U will equal W sub V if and only if W star sub U will equal W star sub V. And that gives us the result. Okay. You can also, if you want to add the condition of strong cospectrality as well, you can also tell when the two vertices are strongly cospectral by looking at the isospectral reduction. And it turns out that if the eigenvalues of the isospectral reduction, so if it has an automorphism, so if they're cospectral, and if the roots of this polynomial are all simple, then the vertices will be strongly cospectral. Okay, just a couple things to point out. In our proof, there was nothing really special about the fact that we were using adjacency matrices. You could apply this to any weighted directed graph that you want to. Yeah, we're not using the fact that it's symmetric or anything. I guess the statement of the theorem looks a little bit different if the graph is directed, but in essence, it's the same thing. I think I'll gloss over that a little. Okay, so there's a generalization of this quantum perfect state transfer called fractional revival. So after we published this paper, I kind of wondered if the isospectral reductions could tell you anything about fractional revival. And basically the same ideas all carry through, just in a little bit more generality. So fractional revival says that in this e to the ITA matrix, the UU entry absolute value squared plus the UV entry absolute value squared equals 1. So this is a generalization of perfect state transfer. It's if the UU is 0, then you have perfect state transfer. And similar to what we saw with perfect state transfer, this boils down to my e to the ita matrix at time t having this block diagonal decomposition here. So there has been some work in developing the theory behind fractional revival. And just like cospectrality is a necessary condition for perfect state transfer, you can come up with similar necessary conditions for this fractional revival, which we call fractional cospectrality. And there are various characterizations of this that are similar to the characterizations we have of cospectrality. So in particular, the walk counts, rather than being equal to each other, they differ by some constant times the walk counts from u to v. The characteristic polynomial of g minus u and g minus v, rather than equaling each other, differ by some constant times this phi sub u v. I haven't really said what that is. It's an important polynomial that comes up in the study of cospectral vertices. And then perhaps most importantly for what I'm going to say in a second, if they're fractionally cospectral, then the restriction of a to the k of my walk matrix to the vertices u and v always commutes with this, this block in the block decomposition of the e to the ita. Okay, so what you can prove, and so this is work subsequent to the paper that I mentioned. This is stuff that I've been working on with an undergraduate research assistant, John Tolbert. But it's pretty straightforward to prove that u and v are fractionally cospectral. Then this matrix has to commute with the isospectral reduction, which boils down to, right, so for cospectral vertices, we needed the two entries in the isospectral reduction to be equal to each other. Now we're allowing them to differ by some constant times the off-diagonal entry. Okay, so we can also characterize fractional cospectrality using the isospectral reduction in a similar way. Okay, so the question becomes, you know, we've come up with this kind of cool characterization of cospectrality and fractional cospectrality. Is this good for anything? Well, it might be, is the answer to that. So the idea here is, say we start with the isospectrally reduced matrix, some 2x2 thing that has the symmetry we want. Could we think through these combinatorial rules that we use to reduce a graph down to kind of reverse engineer a graph that will have that reduction and therefore have the cospectral vertices or the fractionally cospectral vertices that you want? And there is a little bit of progress that we've made along these lines. Most of what I'm about to say is work done by an undergraduate research assistant. John Tolbert is his name. And one important thing is what's called this lambda identity. So for convenience, we're going to abbreviate the function 1 over lambda minus a by just lambda sub a. And I guess the idea here is that this is sort of an easy thing to reverse engineer. So if I have a single vertex with a loop weighted by 1 over lambda minus a, then the directed graph, well, and let's even put some weight on the top. The directed graph that looks like this with you know, something where the weights multiply to the weight on top here along those two edges, and then the weight A on this loop. So this graph will isospectrally reduce down to that single vertex. So if I see, and then similarly, if I have an edge weighted with 1 over lambda minus A, then I can replace it with a path of length 3. And again, I can put a weight here if I want that will have the loop A. So this will reduce down to that, and this will reduce down to that. So if I see things like this somewhere in my reduced graph, I can kind of unfold them into things that look like that. And one helpful thing in thinking about that is this, what we call the lambda identity. So if I have this product of lambda functions divided by a lambda function, and this is the sort of thing that comes up really a lot when you're working with isospectral reductions. Well, if you work through the algebra, it's not too hard. It's a long computation, but it's straightforward to see that this can be expressed as one single lambda function that involves some constants and its own lambda function inside of that. Okay, so as kind of a proof of concept of how something like this might work, start with a graph that you like, that has spectral properties that you like, and compute its isospectral reduction down to something. In this case, we're computing the isospectral reduction down to one single vertex. It's vertex transitive, so it doesn't really matter which vertex. And we get some rational function in lambda. All right, so we take that rational function in lambda and we express it as an expression in terms of these lambda functions, lambda sub something in the numerator and denominator. And then we apply the lambda identity that we mentioned to express that as one single lambda sub something. And so you can think of this as corresponding to a graph with a single vertex, with a loop on that vertex that's weighted by this function. Okay, and then we kind of unfold this in the way that we talked about. So the 3 lambda sub this can be kind of unpacked in this way. So you have the 2 lambda 2 on the weight, and that can further be unpacked into something like this. And then you can think through various ways of expanding out these constants to obtain a bigger 0, 1 matrix, which happens to correspond to this graph. Okay, so I guess the graph here isn't all that interesting, but I guess the point I'm trying to make is oftentimes you can take an isospectral reduction of something interesting and sort of unfold that into something different that will keep some of the spectral properties that you liked about your original graph. Just a couple other examples, and I'll be done fairly quickly. So here's another example of something with some symmetry. So imagine you're starting with this reduced graph. Then you can think through the unfolding of these functions in a kind of similar way and produce a simple graph here. And this graph, so this graph reduced down to these 4 black vertices reduces down to that isospectral reduction. And it turns out that because of the symmetry up here, these 2 vertices here are cospectral to each other. I guess these 2 are also cospectral to each other. That's not quite as interesting because I could already tell that with the symmetry, but here I've produced a non-symmetric pair of vertices that are cospectral. Now, we already knew about this example of cospectral vertices, so I don't know how significant that is, but just as a proof of concept, you can often think through these things. So the question is, you know, these examples I've shown you are in a lot of ways kind of ad hoc. You know, they work out because we were starting with things that we knew should work out. So the question is, can you do this in a very systematic way? That's an ongoing work in progress. The answer to that, I think, is going to be tricky because the answer is never going to be unique. This example shows us that, okay, if I take this graph and reduce it down to these 3 vertices, I'll come up with this. And if I take this graph and reduce down to these 3 vertices, I'll get the exact same isospectral reduction. So whatever unfolding or unpacking of an isospectral reduction that you may come up with, it's never going to be unique. There's always going to be multiple ways of doing that. That's something that I feel actually shows some promise to this idea that, you know, maybe in whatever system that someone comes up with for unfolding something, there will be some choices to make, and those different choices will lead to different families of graphs that may have the nice spectral properties that you want. So that, I feel like, is an important avenue to pursue further. And I think with that, I'll go ahead and stop. Thank you very much.
Thank you. Awesome. Great. Do we have questions for Mark?
So I have a question. Let's say you have 2 fractional cospectral vertices. So we have the walk counts. Can you write down the graph on the 2 vertices? Like, you know how when you do the reduction, you're going down to smaller graphs. So can you write down that graph using the walk counts?
Yes, if you know the full walk count information, if you know the generating functions of the walk counts, then you'd actually be able to write down that 2x2 isospectral reduction. Yep.
Now then, the next question, it's I'm just making a wild guess. So
Yeah.
So you know how you have fractional cospectral vertices, and then the 2x2 matrix, the RS, it commutes with there's a commutivity condition. Okay.
Yeah. Mm-hmm.
Now my question, again, it's totally wild, is that if you take RS, so this is your top block in your diagonal matrix, and if you take the reduction matrix for S bar, so you form a block diagonal matrix, would it be in the adjacency algebra? I'm hoping for too much. It's possible that I have no reason to believe it would, but.
So you want the reductions, let's see, you want the reduction onto the other subset to commute also with whatever matrix it's supposed to commute with.
Yeah, that doesn't happen. But again, it could be too much to ask.
I'll have to think through that a little bit. I think you might actually be right that it does. But I don't know. I'll need to think through it a little.
Can I ask one more question?
Yeah, of course.
It's so you have that strongly cospectral characterization. So you want the 2x2 to be simple, like you have simple eigenvectors as well. I don't know. I might have missed it, but so do you have the same characterization for strongly fractional cospectral?
Oh, you know, the fractionally cospectral thing is something we've done pretty recently. So, but no, I think you're right, because you have some of these same characterizations for strongly fractional cospectrality of the the poles of a certain function being simple, and that will correspond to the roots of these isospectral reductions being simple. So yes, yeah, you will have that same characterization.
Thank you. Well, thank you for a very nice talk. It's a wonderful talk. Yeah.
Thank you.
Yeah.
Good to see you, Ada.
Yeah, good to see you.
We have a question in the chat. So it says, you probably explained this, but what's the relationship between the matrix from the definition of isospectral and the weighted graphs you drew?
Right. So, so if I start with a matrix, right? Any matrix I can write down as a weighted directed graph, right? Right. If this has, you know, some entries, I can write down a graph corresponding to that matrix. So I guess what I'm saying there is that if you kind of have two definitions of the isospectral reduction. You have the matrix definition of applying this Schur complement to the matrix minus lambda I. And you can also view it according to those graph theoretic rules of reducing down the graph itself according to those rules. And so you can reduce down the matrix to a matrix with these functions as its entries. You can reduce down the graph to a weighted directed graph with with weights that are functions in lambda, and those will be the same. This graph will correspond to that matrix. I don't know, is that what the question was getting at? So, and the way to really understand that is via this walk generating function characterization, right? These weights become the generating functions for walks, the non-returning walks between vertices in that subset.
You're saying that the reduction is the Schur complement of the matrix minus lambda I, but it looks like it's the Schur complement of when you take away lambda from the sort of 2-2 block, not from the entire matrix. Otherwise, I'd expect to see an A minus lambda in there somewhere.
Yes, you're right about that. Yeah, you're taking lambda from the block. Mm-hmm. Yeah.
Yeah, I get confused enough about Schur complement at the best of times.
Yeah. Yeah.
Okay, thank you.
Mm-hmm.
I have a couple questions. You said if you start with an isospectral reduction, the graph of an isospectral reduction, and then you unfold it, it's always going to be non-unique. Do you have an idea of how many different unfoldings there are, or how to even what parameters of the graph represent?
I really don't. Yeah, that's something that's still pretty mysterious to me. I don't think I could give you a very good sense of that.
Fair enough. And then my other question was just the second unfolding you showed of the reduction from the Peterson graph. What is the spectrum of that graph?
You know, I actually had this written down and I decided not to include it in because I didn't want that to take up too much time.
Sorry.
It's not the exact same as the spectrum of the Peterson graph, but really what happened here is this actually is the divisor matrix for the distance partition of the Peterson graph. So the eigenvalues that come from that equitable partition are the same. And it's kind of cool. The rest of the eigenvalues, if I'm remembering right, a lot of them are just the negatives of the eigenvalues of the Peterson graph. And I don't really know how to explain why that's true. That might just be a coincidence, but in a sense, the kind of important eigenvalues that are coming from the equitable partition are preserved.
Right. Cool. Any other questions?
I have a question.
Mm-hmm.
So you sort of, you had this theorem where you sort of characterized the cospectral vertices using these hidden symmetries.
Mm-hmm.
It's very nice. I like that. And I was gonna ask actually what you can say about the strongly cospectral vertices, which you did answer that question. I was just wondering, is that something that like, is the proof of that, does it come from the proof of the other thing, or like, is it an easy implication, or?
That is a very easy implication. Well, if you have all the right tools. So I think Chris has this paper, I think it's called Strongly Cospectral Vertices, where there's a characterization that if the poles of a certain function are simple, then the vertices are strongly cospectral. And basically the determinant of the isospectral reduction minus lambda I is basically just 1 over that expression. And this follows from a lot of the literature that already exists about isospectral reduction. So it just happens that all the tools align just right, that that it's a pretty easy implication, yeah.
Okay, nice.